it is the system to be applied in transmission system to power system. It is called flexible AC transmission system. Using this system, we can make the system, the transmission system into a flexible one. That's why it is flexible AC transmission system. So the definition for FACS, alternating current transmission system, incorporating power electronic base and other static controllers to enhance controllability and increase power transfer capability. So using the devices, the so-called FACS devices, so they can improve the capability of the power system, especially the transmission system. So the devices used in FACS system is known as FACS controller. It is a power electronic based switching devices. The FACS controllers are power electronic based the switching devices, a power electronic based system and other static equipment that provide control of one or more AC transmission system parameters. Using this switching device, we can change the transmission system parameters like voltage, current, power. It is power to real power and reactive power, the voltage magnitudes, the voltage angles, everything we can control using these switching devices, FACS controllers. The benefits of FACS technology: control of power flow as ordered. So power flow, whether it is real or reactive power, the power is being controlled by the FACS devices. Increases the loading capability of lines. So we are extending the lines according to the load requirement. We are extending the number of lines. So using the FACS technology, we can increase the capability of lines, and also we can enhance the thermal capabilities. We can increase the thermal capabilities of the system. Increase the system security through raising the transient stability limits. So we are increasing the security level of the system by increasing the transient stability limits. The transient stability means the stability of the system withstanding for sudden high changes. So in that we can increase the transient capability of the system, that is the security of the system, by enhancing the transient stability of the system. It provides security tie line connections. So we have tie lines. Tie lines means the lines connecting the transmission system of two or more different power generating systems by means of these tie line connections. So it provides the secure tie line connection to neighboring utilities and regions, thereby decreasing the overall generation and reserve requirements on both the sides. So the sharing of the power on both the sides, it is also possible by using this FACS technology. Provide greater flexibility in single new generation. So flexibility of greater flexibility in cycling new generation. So new generations, it can be possible by this FACS technology. Reduce reactive power flows, thus allowing the lines to carry the more active power. So it reduces the reactive power flow. The main function of the FACS devices is the compensation of reactive power. So we are reducing the reactive power flow, thus allowing the lines to carry more active power by reducing reactive power. And also we can increase the reactive power. If it is the system is of shortage of reactive power, we can add reactive power within the system by using this FACS devising technology. It increases the utilization of lowest cost generation. So it is the cost of generation. Cost of generation may be reduced by using this FACS technology. So what are the devices? Series controllers. So series controllers, the FACS devices which are being in series with the system for controlling the various power system parameters. Similarly, we have the shunt controllers. They are parallel to the lines, and the combined series and controllers. So here we have the FACS devices both in series as well as parallel connections. It's a combination of series as well as the parallel combination, using which we are controlling the reactive power. So it is the series shunt controllers. We have the series and shunt controllers. So variable impedance based static shunt compensators. Variable impedance based. So using FACS devices, we are varying the impedance of the system, impedance of the lines. So line impedance is depending upon the resistance as well as the reactance. So using the FACS devices, we can change the impedance of the system using static shunt compensators. So what is static shunt compensators? The shunt connected controllers, static synchronous generators. So they are all shunt connected controllers. Static synchronous generators, static synchronous compensators. In short, it is STATCOM, abbreviated as STATCOM. Battery energy storage system, BESS. Superconducting magnetic energy storage. Static war compensator. Static war means the reactive power. Voltage, ampere, reactive. They are compensating. Especially reactive power compensation. This device is being used. Thyristor controlled reactor. So using which we can change the reactance. So generally reactance means it is inductance. Here it is referring the inductance. Thyristor switch resistor, thyristor switch capacitor. Same here. Using the switching device, we are varying the capacitance of the system. Static or generator or absorber. Thyristor controlled braking resistors, TCBR. These are all the various shunt compensators. Here we are using the variable impedance, using which we are varying the impedance of the system. Either impedance means either resistance, inductance or capacitance, capacitive reactance or inductive reactance. The first one, static synchronous compensator, abbreviated as STATCOM, static synchronous compensator. It is fax devices, so used for compensation. Compensation here is the reactive power compensation, mainly reactive power compensation. In addition to that, using this STATCOM, we can compensate the real power too. So having a battery energy storage here, we can have the backup of real powers, so that we can use the required real power for the transmission system. So it is a static synchronous generator operated as a shunt connected static war compensator whose capacitive or inductive output current can be controlled. So here capacitive and inductive output current can be controlled independent of the system voltage. So without any change in voltages, we can make changes in capacitive or inductive output current using these devices. STATCOM based voltage source converters and STATCOM based current source converters. So two types of STATCOM based devices, voltage source and current source. Next one, static war compensator. It is one more shunt compensating device, static war compensator. So static, giving a static control over the power system parameters. VAR represents voltage ampere reactive. That means the reactive power compensation, reactive power compensation. It is a shunt connected static war generator or absorber. So why it is generator or absorber? So generators means it supplies the reactive power. Absorber means it absorbs. So generators supplies, absorber absorbs the reactive power. So this SVC can be operated either as a generator or absorber, whose output is adjusted to exchange capacitive or inductive current so as to maintain or control specific parameters of the electrical power system, typically bus voltage. So mainly the bus voltage can be varied using this SVC. So it is the schematic representation of the SVC, static war compensator. The thyristor controlled reactor TCR or thyristor switch reactor TSR for absorbing reactive power, and thyristor switching capacitor for supplying the reactive power. So normally capacitor is having supplying of reactive powers. So TCS is being used as a generator. The other devices TCR and TSR for absorbing the reactive power. They are inductive reactive devices. SVC is considered by same as a low cost alternative to STATCOM. So we can use SVC as an alternative to STATCOM. So what is the difference here? So both are shunt compensating device. So here it is cost effective. SVC is cost effective, and also it controls the reactive power. That is either capacitive reactance or inductive reactance. Next one, variable impedance based static series compensator. Here also we are changing the impedance. Impedance means resistance, inductive reactance or capacitive reactance. Based static series compensators. So they are being connected in series with the system. So they are series compensators. So what are the various series connected controllers? Static synchronous series compensators, SSC, interline power flow controller. So they are controlling the power flow within the line, interline, in between two lines, IPFC, thyristor controlled series capacitor, TCAC, Thyristor switch series capacitor TWC. Thyristor control series reactor TCSR. Thyristor switch series reactor TSSR. So various series connector controllers using which we can change the impedance of the system so that we can control over the power system parameters. What is RAJASEK? The specific function of the RAJASEK. It is in a static synchronous series compensator. Output voltage is in quadrature with and controllable independent of the line current. So here we are varying the voltage for the purpose of increasing or decreasing the overall reactive voltage drop across the line. So reactive voltage drop. So we have voltage drop in the line using which we can compensate the voltage drop. Here we can change the voltage, either increase or decrease the voltage. So it is like a start comp except that the output AC voltage is in series with the line. So here the AC voltage is in series. It is a difference. In start comp it is in series. The output AC voltage is in series with the line. TCAC, the next device. TCAC is a series compensating fast device using the control power flow in transmission lines and improve transient stability in the power system. The specific purpose of TCAC is enhancement of transient stability in the power system. And also it controls the effective line reactance by connecting a variable reactance in series with the line. So it controls the line reactance by connecting a variable reactance in series. It may be inductive reactance in series with the line. So the schematic diagram of TCAC. Thyristor control series capacitor. So it is the capacitor connected in series with the system. And also we have inductive reactance here in series with anti-parallel connected the thyristors. So switching devices. So using which we can control the voltage on the system. A TCAC is typically made up of the following major components: a series compensating capacitor, say bypass inductor. So L is a bypass inductor. Bypassing. It is bypassing the current, not allowing the current through the capacitor. It is bypassing. Back-to-back thyristors. The two thyristors, back-to-back thyristors, SW. The degree of TCAC compensation is controlled by the size of capacitor. So by varying the capacitance, we can change the degrees of compensation. Thyristors are used to transform the equivalent impedance of the TCAC, which fulfills the need in improving the stability, increasing the transmission stability. So that we can increase the transmission capability of the system. Restraining hyposynchronization, resonance, etc. So it also avoiding the hyposynchronization. So synchronization. So it is very, very important. So avoiding the synchronization between the reactants of the systems, so that we can avoid the resonance. So if resonance will be taking place, the capacitive and inductive reactances are being equal, so that the system is nil resistive system, so that we have the high current, high voltage on the system. So it should be avoided. The resonance, synchronization, resonance, it should be avoided. The basic idea behind the power flow control of TCAC is to increase or decrease overall line effective series transmission impedance, changing the transmission impedance by adding a capacitive or inductive reactance. In capacitive mode, TCAC reduces the transfer reactance between the buses at which the line is connected and increases the maximum power that can be transmitted. This is the purpose of the connected series capacitor. TCACs that have a parallel LC circuits. So here we have one more. L is parallel to C, consisting of a fixed capacitive impedance XA and a variable inductive impedance X. That is, the reactance of the TCAC is being given in the following equations. So it is thyristor valve, bypass mode, inductive region. The various modes of using various switching modes for various switching angles. So what will be the characteristics of the TCAC? Next one, the third one is partially conducting thyristor Vernier mode. So what is partially conducting? So it is only partially conducting, only for certain conditions. This mode allows the TCAC to behave either as a continuously controllable capacitive reactance or as a continuously controllable inductive reactance. So it may be capacitive reactance or inductive reactance. It is achieved by varying the thyristor pair firing angle in an appropriate range. A smooth transition from the capacitive to inductive mode is not permitted because of the resonant region between the two modes. So the smooth transition is not possible here for avoiding resonance. So the two modes here are capacitive vernier control mode for changing the capacitive reactance. The next one is inductive vernier mode. It is for operating the system in inductive reactance mode. So we have to operate the system either in capacitive vernier control mode or in inductive vernier mode. There are two modes, capacitive vernier as well as the inductive vernier mode. Modeling of DCAC. So we have to model the mathematical modeling of DCAC. So according to our requirements, we can model that DCAC, resistor control series capacitor. So being operated in either modes, capacitive modes or inductive modes, we can model the DCAC, various mathematical equations for DCAC. So the applications of DCAC. DCAC is used for improvement of stability system. So like SVC, using this system also we can improve the stability. So how it withstands the abnormal conditions, the fault conditions, that is called stability. So using DCAC we can improve the stability of the system. And also enhancement of the system damping, system damping. So damping of oscillations. So oscillations is due to the reactance changes within the system, the reactive power compensation shortage. So using which we can have the damping of the system. The damping can be avoided by using this DCAC. So various oscillations. Using DCAC we can stable the system without oscillations. We can damp the oscillations within the systems. So next one, converter based compensators. Converters based compensators. So static synchronous compensator. So previously we have a shunt compensating device, SVC. Here it is static shunt compensator. So here the difference is it also supplies the real power. The shortage of real power can be supplied by using this StatCom. But in SVC it is not so. It is only compensating the reactive power. But StatCom controlling both real as well as reactive power on the system. So it is the schematic of the StatCom. So utility, the transfer system using transformers. Here stepping down the voltage. Here we have anti-parallel radiators here, and also the battery source, using which we can supply the requirement of real power to the system. So if it is short of real power, it can be supplied from the transfer system. From the system it is being supplied. So whenever the system requires the real power, it can be supplied by the battery backup of this StatCom. So it is the schematic of the StatCom. The operating modes. It is also operated in capacitive or inductive modes for various firing angles. Next one, unified power flow controllers. Unified power flow. So unified power flow controller is also for controlling both real as well as reactive power. But here we have the two compensating device. In StatCom only it is a shunt compensating device. UPFC, here we have both series as well as shunt compensating device. So one is in series, other one is in parallel. There are two converters. So one is in series, other one is in parallel. So using which we are controlling the various power system requirements here, the various modes of operation. The UPFC operates with constraints on the following variables. The series injected voltage by load. It can using which we can inject the series voltage. The line current through series converter. Line currents can also be varied. The shunt converter current. The minimum line side voltage of the UPFC, the maximum line side voltage of the UPFC, and the real power transfer between the series converter and the shunt converters. So these are all the operating modes of the UPFC. Static synchronous. This one is static synchronous series compensators. That is SSC. So it is another compensators. Here also we have the two types of compensation, but here especially it is series compensation. So using this compensator also we are compensating real power as well as reactive power. So VI characteristics of the SSC. Basic two converter scheme for IPFC. So here also we have two basic converters. So two converters. So interline power flow controllers, we are having number of converters, n number of converters here, using which we can have so many advanced applications in the transmission system. So generalized IPFC, which can be operated as a STATCOM, SSC, UPFC or IPFC. So using IPFC, we can operate the system as a STATCOM, SSC, UPFC or IPFC. So having so many converters, so we can have this so many charges. We can operate the system in series, in shunt, and also compensating the reactive power over the system. Okay, installation of fax converters, coordination aspects. So the coordination between the various controllers. So here we have so many controlling devices. It may be series controllers, shunt controllers, combined series as well as shunt controllers. So the coordination between all the controllers is very, very essential. So here we have coordinating all the controllers. So what are all the difficulties in having so many controllers in system, and how to overcome the various unwanted effects on the system. That is using interactions, we have so many. So the frequency ranges of the different control interactions have been classified. 0 Hz for steady state interactions, 0 to 3 by 5 Hz for electromechanical oscillations. So these are the variations will be taking place in the system. So we have to avoid all the interactions over the various controllers in the transmission system. So control of small signal oscillations, subsynchronous interactions, subsynchronous SSR. So having reactance of capacitive and inductance, we are having the possibility of occurrence of resonance. So that should be avoided. And also we have high frequency interrupts. So all the unwanted effects can be coordinated and be controlled by this coordination of the devices. So here we have two SVC. Two SVCs are currently here. The interaction is taking place between the two SVCs, SVC1 and SVC2. And we have this coupling, how to coordinate the multiple controllers using the control techniques, the mathematical modeling, so using which we can arrive a solution avoiding the interaction taking place between the two controllers. So that is complete the portion of 30 students fax devices. So the main purpose of fax devices is the reactive power compensation. It is a power loading based fax devices using which, having series as well as shunt, the combination of series as well as shunt, we can control the various parameters of the power system. So normally it is reactive power compensation. Why? Because the reactive power is depending on the voltage, the main parameter of the system. So using reactive power compensation, we can control over the voltage. And also in some devices, we can have the back power of real power, using which we can compensate the real power of the transmission system. So with this, let us complete today's session. Thank you, students.